So the seminar will be made available through social media and also the college website. This is our first seminar in the seminar series in fall 2021. And the seminar is given by Dr. Hanyi Yang, who is a postdoctoral researcher in civil engineering. And Dr. Yang got his PhD in civil engineering from Illinois Institute of Technology, and also his master's degree in civil engineering from University of Connecticut. The Dr. Yang's research is mainly in the intelligent transportation system. He also studies the traffic flow theory, traffic control, deep learning, and things related to intelligent transportation systems. Today, he's going to talk about his most recent research in network topology-based deep learning approach for traffic speed evolution prediction. Without further ado, I guess I'll hand it over to Dr. Yang, please. And you may start your presentation. Yes, please go ahead, Hanyi. Yeah.
Okay, no problem. Good morning, everyone. I'm Hanyi Yang. I'm a postdoctoral fellow in the civil and environmental engineering. Right now, I'm working in the Dr. Guohui Zhang's research group. I'm very glad to have this opportunity to talk about my research. This is my just finished the paper. The title of this topic is network topology based deep learning approach for traffic speed evolution prediction. From this title, we can say that it's about the traffic speed prediction. The traffic speed prediction is a very traditional topic. It has a very, very long history. And also from this title, we can say that it's network topology based. Because this, then we can know that this topic is related to the network structure. Here we refer to, here it refers to the topologies, the network topology structure, the road network topology structure. Here we got to consider the traffic dependency among the different road sections in a network. About the traffic speed prediction, this topic has been studied for a long time. But different researchers has different definition about the traffic speed. So it can be studied in different perspectives. In my study, in my research, I study it in the perspective of traffic engineering. So the definition of traffic speed is in the definition related to the traffic engineering. Okay, now let's talk about my study. Before we study the traffic speed evolution, first we need to define what is the traffic evolution. In this study, the traffic evolution refers to the traffic state variation in a space area as time elapses. That means here the traffic state in the field of transportation engineering or traffic engineering, the traffic state can be illustrated by three important characteristics. They are traffic speed, traffic flow, and traffic density. There is a relationship among these three characteristics. That is the traffic speed equal to the traffic flow divided by the traffic density as for a location and a time. Here we can say that the traffic, all of these three variables is a function of time and the location x. T refers to the time, x refers to the location. Here we can, from this we can say that this topic will talk about the traffic state variation in the temporal spatial area. Thus, in this study, we will talk about the evolution of this kind of function with time and space in the temporal space area. Comparatively, the traffic speed is more difficult. It's more important than the other two traffic characteristics, traffic flow and the traffic density. The first reason is that most of our road users care more about traffic speed. We care more about how long I can drive to my home, or how long I can drive to our destination. So traffic speed is more popular. In addition, the traffic speed is much easier than the other two variables to be obtained, because we can a lot of equipment can measure the traffic speed, but for the others, we need some more complicated equipments to do that. And even for traffic density, perhaps we need to estimate them. We cannot directly observe it. In the previous study, the traffic speed prediction includes three important stages. At the early time, the statistic methods were more popular because of the traffic data has the time series properties. For example, it has two peaks during the weekdays and one peak during the weekend. For example, for a weekday, we have a morning peak hour and the evening peak hour. So because of this property, in the very early stage, statistical methods were more popular. But this method cannot deal with the high dimensional data. Because we need sometimes if we want to do some transportation planning or to do some vehicle routing plan, we got to consider the whole
something like Chamberlain, right? Yeah. Chamberlain Hyper. You should just input it into yours too. Here you go. Sharing it. Thanks, Nick. Are you still doing homework?
Oh yeah.
What?
Okay, I will continue. We need to consider the different road sections in a road network. Thus, the early method, the static method, is not enough to solve this kind of problem. Then later, some classical machine learning methods were used to predict the traffic speed. Although this kind of method can solve the high dimensional data, but they didn't consider the traffic dependency, because we all know that in a road section, like this one, the traffic on road section 5 is impacted by the road section 3, 4, or 6, 7, this kind of things. But this kind of classical machine learning method cannot solve this problem. And then in recent years, some deep learning methods were used to analyze the traffic data dependency. When we predict the traffic speed evolution, traffic speed in a road section, we got to consider the variation of the traffic speed on the other road sections. But this kind of method only analyze the traffic data dependency instead of the real physical dependency. For example, if we study the traffic evolution on road section 5 here, we need to consider the traffic state on road section 3 and how much traffic flow it will enter into the road section 5 in the next time step, this kind of things, or whether the downstream will occur traffic congestion, whether it will impact the upstream like the road section 5. This is also important property to help us to do some traffic management. Then all this method cannot solve the emerging problems. In addition, in all these previous studies, they only analyzed the point traffic speed prediction, but it didn't consider the traffic evolution. Because the traffic evolution is more related to traffic physics, it is very useful in the traffic control. Thus, in the previous method cannot solve this kind of problem. Then there exists the research gap. The traffic, they include the traffic evolution on road network and the physical interaction among the traffic on different road sections in a network. This study is very important in future related study. For example, it can be useful in the connected and autonomous vehicles motion plan, this kind of research. And they can be used in the proactive traffic management and the electronic vehicle real-time energy usage management, and so on and so forth. Now let's talk about my problem. Before doing that, we got to first define what the problem is. First, we need to, because the traffic variation is a very complicated problem, it is very difficult and even impossible to give a closed form function to describe the traffic evolution, to describe traffic evolution. Thus, we got to describe the traffic, the time and the space to analyze, to regard it as a discrete problem. Then in this study, we will predict the next worldwide traffic speed evolution at each discrete time step with a uniform interval delta t. Here we also assume that we can obtain the traffic trajectories data. They can be provided by the probe vehicles, such as the connected vehicles. Also, we assume that we have the point traffic data. This kind of point traffic data can be given by the point sensors, like the loop detectors or the cameras. This kind of fixed point data are often collected at the ends of a road section. Okay. Now, let's in the next step, we got to split a road network into a series of homogeneous closed road section. This is because the existing theoretical method about the traffic evolution can only be suitable to closed homogeneous road section. Then, if we want to study the traffic speed evolution in a road network, we got to separate them into small closed road section and study them separately and integrate them together. Here we assume that we will predict the traffic speed evolution in the next time interval capital T. It is equal to the h1 times delta t. Here the delta t is the data update interval. Then that means we will predict the future h1 time steps. Now we also need, because we need to consider the traffic dependency, we need to define the neighboring network for a road section. For example, as for the road section 5, the road section 1, 2, 3, 4 is upstream road sections, and the 6, 7, 8, 9 are the downstream road sections. So we got to define the upstream road side and the downstream road side. Here we got to consider both of them because the upstream traffic will enter the road section 5. We consider the downstream road sections because if traffic congestion occur in the downstream road sections, that this kind of congestion traffic state may propagate back to our objective road section. Thus, we got to consider both of them. Now, after analyzing the road network, right now we got to focus on road section. Here we assume that we will study road section S. Just as we discussed, the traffic variable is still very complicated in the spatial dimension. So we got to divide the spatial dimension into small cells. Here, the road section S is split into NS spatial cells with a uniform length of delta LS. Now, in this study here, we got to define what is traffic speed. Here we will assume that in a cell, that is the cell in the temporal spatial area, it has many rectangular cells. In each cell, the traffic state is constant and homogeneous, and the definition of the traffic speed is the total travel distance divided by the total travel time. Here, the total travel distance means in a small cell, all the travel distance, the summation of all the vehicles travel distance. The total travel time means in this cell, the summation of the summation of the travel time of all the vehicles in these cells. Then we have the definition of the traffic speed. After having that, we have the road speed. The road speed is the road speed can be represented by a vector. It is a NS dimensional vector. Then okay. After having it, we can also have the neighboring traffic speed that can be represented in this formation. It includes the traffic speed on itself, on its upstairs road sections, downstream road sections. Then this study will seek to develop an approach to predict the high-resolution network traffic speed profile within a prediction horizon H1. That means we will predict the future H1 time steps using the input including the known network speed. That can be represented by this formation, by this equation. Okay. Next, let's talk about the research challenge in this study. First, we need to build up a framework to integrate the traffic speed evolution estimation method and the neighboring traffic dependency analysis. Because we got to analyze both the traffic evolution on every road sections. We also need to consider the traffic dependency among these road sections. Also, the neighboring traffic speed vs traffic is very difficult to be captured by the traditional mathematical approach because it involves the complicated temporal spatial dependency among traffic flow on different road sections. So we need to solve this problem. Finally, when we collect the field data, it involves various errors such as the missing data, the corrupt data. Thus, we need to find a method to overcome the impact of this kind of errors. This is the structure of this study. In this study, the core part is the state transmission model. It illustrates the traffic dynamic process, the traffic speed evolution. And in order to apply this this model, we need to initial condition and boundary condition. As for the boundary condition, we will use the recurrent neural network to predict it. Here in this model, we got to consider the neighboring traffic speed on the neighboring network. When we do that, we need to consider the road network structure. We need to analyze the traffic dependency. Also, we still need initial condition. Initial condition, there are two sources data information. Through two sources information, we can get the initial condition. The first one is if we assume that we are at the time step k, the traffic speed, the initial condition means the current condition, the current traffic speed can be predicted at the previous time interval, time step. That means we can, if we want, we have the traffic speed at the current time that can be predicted at the one time step, one previous time step. This is one source. Another source is the real collected data. We can, because we have probe vehicles, we have connected vehicles, they can provide us with vehicle trajectory information. We can, through that, we can get the traffic speed. But both of them have problem. So thus, we need to do some data imputation, data assimilation to get the initial condition. Both of them can be applied to the state transmission model. Then we can predict the traffic speed in the next time step. And when we arrive at the next time step, this result will still be need to be taken as input of data assimilation stage. And this can tell us the future. We can repeat this process step by step, and then we can predict the future traffic speed. Now let's first of all, let's come to a road section. We got to study the traffic speed evolution on a closed homogeneous road section. This can be described by a partial differential equation. It is called the LWR model. This model comes from the conservation law. From this model, we can see that it is the relationship between the traffic flow, traffic density with respect to the time and the location. But our problem is to predict the traffic speed. Thus, we got to transfer, convert it to the velocity version of the partial differential equation. Here, we assume that the traffic factors follow the Green-Shields model. That means we assume that the traffic speed and the traffic density has have this relationship. In this equation, the VF refers to the free flow speed, rho G refers to the jam density. Free flow speed, that is, we can we can temporarily regard it as the largest speed on a road section. And the rho, the jam density means all the vehicles parked on a road section. No vehicle, the vehicles cannot move forward. This scenario, the density corresponds to it. Because previously we have this equation, we have the identity equation, the relationship between traffic speed and traffic flow and the traffic density. Then we can have the velocity version, the partial differential equation, this one. This partial differential equation is very difficult to be solved in a closed formation because it is a nonlinear equation. Thus, a numerical method is perhaps more suitable for this problem. In this study, we used the Goodenough scheme to solve it. After applying the Goodenough scheme in this partial differential equation, we can get this state transmission model. This is the solution of the previous partial differential equation. Here, we can say that we can use this equation to estimate the traffic evolution if we have the initial condition and the boundary condition. Then our next task is how to estimate the initial condition and how to predict the future boundary condition. Then the initial condition means the current traffic state. So then if we have the future boundary condition, then we can use this equation to calculate the traffic evolution. It is called the VCTM. It means the velocity variance CTM. CTM model is referred to the cell transmission model. It was developed in 1994. It is a very important traffic flow model in the field of traffic engineering. Now let's talk about the boundary condition modeling. Here we got to consider the temporal-spatial traffic dependency. In this, to analyze the temporal-spatial traffic dependency, here this study used the graph theory and the dynamic programming to solve it. We develop a graph theory and a dynamic programming based algorithm. In this step, first we got to convert a road network into a connection network. Here, this one is a road network. We got to convert it into a connection network. We got to label every road sections. They have their own index. And then in the connection network, will illustrate the relationship among these road sections. For example, the road section 1 is directly connected to the road section 3. In the connection network, node 1, node 3, they represent the road section 1, road section 3. 1 directly connect to 3. Then, according to this law, we can draw the connection network. In addition, after having the connection network, we got to write its mathematical representation. That is an adjacent matrix, A0. In this matrix, all the rows, all the columns corresponding the index of the nodes in the connection network. That is, they are also the index of the road sections. If two nodes are directly connected, for example, one can reach 3, the corresponding entry will be 1, otherwise will be 0. Then the 0 order adjacent matrix tells us the direct connection relationship. Perhaps two nodes are indirectly connected. For example, 1 and 5, they can be connected through node 3. Then we can multiply them to get a higher order adjacent matrix to represent this kind of indirect node connection, node dependency relationship. And we can do it until all the entries of the order of I are 0. That means for this matrix, all the entries are 0, we will stop. Then we can have a set of matrix, and they represent the spatial relationship of all the road sections in a road network. Right now we have the spatial relationship among all these road sections, and we got to consider the temporal relationship. Here, for example, we can know that the traffic on road section 5 can immediately be impacted by traffic on road section 3. The traffic on road section 3 will continuously enter into the road section 5. Then then the traffic on road section 3 impact road section 5 immediately. There is no traffic propagation delay. But for road section 1 and road section 5, the traffic on road section 1 need to spend the time through road section 3 and get into the road section 5. So we got to consider the traffic state propagation delay. In order to solve this problem, we need to define the cost of each road section. That means the cost on each node in the connection network. It can be defined as the length of the road section divided by the free flow speed on the corresponding road section. Then the temporal dependency between two nodes becomes the shortest path problem between Ig. Here we define, in this connection network, we define the cost on the link is 0, because the link in the connection network just represents the relationship instead of the real distance. The cost on the node is the traffic state propagation time. That means because when we pass through a node, we need to spend some time to do that. To solve this problem, we can use a dynamic programming, and then we can solve the corresponding the traffic propagation time, corresponding traffic propagation time to the node, to the matrix A. The matrix A represents the spatial relationship. The matrix tau represents the temporal relationship. Then after having that, we can have the temporal spatial relationship among the road sections in a network. After having that, we got to predict the boundary conditions for every road sections. Here, for each road section, we built a LSTM model. And the input of this model is its neighboring traffic speed. And its output is the boundary condition of itself. For example, right now we are at the end of time step. We are at the end of time step K. We want to predict the boundary condition in the k+1 time step. Then we got to take the input of the current traffic speed on this road section, and its neighboring the traffic speed on its neighboring network. But how to select the neighboring network traffic speed is important. Here we got to consider the traffic delay. So, for example, we want to predict the boundary condition of road section S. We got to consider the traffic. If we are at the time step K, we got to consider the traffic state on road section 1. The time step need to be a little bit earlier. The difference, the delay, is the traffic propagation time on the road section 3. Based on this idea, here we define the input of the LSTM model. And through this, we can predict the boundary condition. And this boundary condition can help us to predict the next steps traffic state on the whole network. And this can also be taken as the input of this LSTM model. And we can further predict the next step, the next step boundary condition, and we can estimate the corresponding traffic evolution. We can repeat this process to the our prediction horizon. Then up to now we have the boundary condition. We also need the initial condition. Here we assume that we are at the end of the case time step. Then we have two sources of traffic information, traffic speed information. One is the VSK that can be predicted at the k-1 time step. Also, we can observe traffic speed through the probe vehicles or connected vehicles, but both of them are not accurate enough because this estimate, the predicted traffic speed comes from the theoretical model. The theoretical model, there are a lot of assumptions in the theoretical model. They cannot completely reflect the real traffic scenario in most cases. So it will cause errors. Also, because right now, not all vehicles are connected vehicles. Thus, then we can only get part of the vehicle trajectories in each cell. We use the traffic speed calculated by the observed vehicles, part of the vehicles, to represent the whole vehicle, the speed of the whole vehicles. It still can cause errors. Then we need to find a method to simulate these two sources of data. In this study, we use the extended command filter to overcome this problem. The extended command filter is an optimal sequential data assimilation method developed for nonlinear dynamics and measurement precise. It is suitable for the nonlinear precise because our formulation is our equation is nonlinear because we have at least two traffic states, the free flow state, the congestion state, and they need to from one state transfer to another state, this kind of thing. So it is a nonlinear problem. This is the extended command filter process, and in this procedure, we got to calculate the Jacobian function, Jacobian matrix. It is an important factor in this procedure. This need to be calculated by depending on our state transmission model. Thus, this study developed the corresponding Jacobian matrix is in this formation. In this matrix, most of the entries are 0 except the places around the diagonal, like this. Next, when we collect the traffic data, when we collect traffic data, this data can often run into some problems, such as we have missing data or we have the corrupted data. This kind of data cannot be used directly. They need to be dealt with. In this study, we use a feed-forward neural network to solve it. And in this, as this feed-forward neural network, the input includes the historical traffic speed data in the cell at the same time step, and the traffic speed observation at its upstream cell and the downstream cell, as well as the estimated the traffic speed from the previous time step. And then we can get through this fitting process, we can build a method to build a model. We can build a model to fit the relation to correct the traffic speed, to correct the traffic speed data. Finally, this is the experiment. In this experiment, the test bed is a road network close to the Seattle in Washington State. In this road network, we have 7 road sections, and we can collect the loop detect data from it. This data from November 1st to December 31st in 2015, and the data collection interval is 5 minutes. In this study, we convert this data to the trajectory data by the software vision. And here we use the first 6 weeks as the training set and the others as the testing set. This is the parameters of our method. First, we need to determine the free flow for each row sections. Here we use the green shield model to fit it on each row section, and we use using historical data. The free flow speed is the traffic speed corresponding to the traffic density is equal to 0. And the traffic speed prediction update interval is set to be 5 seconds. Here in the LSTM model, we set the look back time step is 600, and we will predict the future 30 minutes traffic speed evolution. Here in this study, the parameters are shown here. They include the feed-forward neural network parameters. It includes this feed-forward neural network has three layers, and the LSTM model still have 3 LSTM layers. Each LSTM layer has 200 cells. Yeah. The evaluation matrix in this study, the evaluation matrix the matrix include the root mean square error and mean absolute percentage error. This figure illustrate these 2 figures illustrate the average performance of the proposed method. We can say that in the prediction horizon, the mean absolute percentage error can range from 2% to around 14%. As the prediction horizon increasing. And here we also analyze the effect of proposed data imputation method. Here, in this experiment, we use two methods to imputate the data. The first is use the forward neural network. The other is we just use the historical mean to represent to replace the missing or corrupted data. Here, we selected 0.1% of the connected vehicle data are replaced by a random number between 100 miles per hour and 200 miles per hour. Because in most cases, the traffic speed cannot reach this value. It's so it is corrupted data. From this figure, we can see that the performance of our proposal method is better than just use the historical mean to replace the corrupted data or missing data. The solid curve is our method. The dash curve is just use the historical mean. We also analyze the impact of the connected vehicle penetration rate on the prediction performance. Let's look at this solid curve. We can say that as the increase of the connected vehicle penetration rate, the mean absolute percentage error decrease. And when the connected vehicle percentage reach 30%, the performance of our method is stable. That means if we have more than 30% of connected vehicles in a road network, that can accurately reflect the real traffic scenario. We also studied the effect of the traffic dependency analysis. Here, it includes two parts. The difference of this experiment is that the LSTM has different input. When we consider the road segment dependency, we got to take a neighboring network speed as the LSTM input. If we don't consider the road dependency, we just use the traffic speed on the road itself as the input. So our experiment shows that if we consider the road section dependency, it has a better performance. And finally, I also compared our method with the other baseline algorithm. The selected benchmark methods include a traditional time series analysis method, ARIMA, a basic machine learning method, support vector regression, and a deep learning model, GRU. From the experiment results show that using the deep learning method is much better than the others. And the difference between these two methods is not very apparent. It's not very clear because these two methods are too similar. This is my idea, my opinion. Okay, this is my study. Thank you for your attention. Any questions?
All right. Thank you, Dr. Yang, for the presentation. Any questions from the audience? When you do the estimation, you use an extended common filter technology. What are the measurements you're using as an input?
Yeah, it includes two inputs. The first one is, for example, right now we are at the end of the case time step. Here we can now we have the traffic speed on a road section. This traffic speed can be predicted at k-1 time step. This is one source. This is the estimated result. Another result, because we are at the end of the case time step, we can collect the traffic speed data from the connected vehicles of the other proof vehicles. This is another data source. We got to assimilate them together. So they are taken as the input of our extended common filter.
Oh, I see.
One is a theoretical result, the other is a real observation.
So okay. So how heavy is a computational load if you are dealing with a lot of cars, for example? Then what is the latency? Because you probably need to do this in real time, right? So
Yes.
what's the time delay?
The time delay is just use the around the point 0.3, 0.4 this order. 0.3, 0.4 the second around this level. Because after having this kind of equation, it's not a very difficult calculation. Just the multiplication and add and minus, like the kind of things.
Right, yeah. So okay. So with this, so if you use a AI, a neural network, would this be only specific to a specific route, like specific road, the condition matter?
Yes, this method for each specific road section, we got to build up a specific neural network for it. Because for each specific road section, its neighboring road network is different from the others. So we got to consider the road network structure for each road section.
Right. And then would seasonal changes of traffic pattern affect?
Yeah, exactly. In fact, it has a seasonal impact. But in this study, we didn't consider it because we have a lot of factors need to be considered. Last in this study, we didn't add it. But in the previous studies, some guys considered the seasonal factor, the impact of seasonal factors on the traffic speed prediction. Because different and even weekdays and weekends, we have different traffic formation on our road network.
Yeah. Thank you. Any other questions?
Yeah, I have a question. And mind you, I'm coming in from a different discipline, but I'm assuming that in an implemented form, the calculations that were performed happen local to the section of road, and that information is available to host autonomous vehicles or other vehicles that want to take it locally and determine speed from that. Is that kind of the implementation method?
Yes, I think so. It can be, excuse me. This kind of information can be sent to some autonomous vehicles. They can, according to the future traffic speed evolution to design their speed, and even their routing plan, this kind of things.
Okay, so if the S section upstream 7 or 8 sections away suddenly reaches a 0 velocity because of a traffic incident, that information is computed upstream to the vehicles heading in, knowing full well that they're going to have to stop, and it reduces potential multi-car crashes, that kind of thing, correct?
Yes, exactly. I think so, because it is more useful for the upstream vehicles, but here we got to consider the downstream scenario, because perhaps the upstream traffic, if the upstream traffic reach a threshold, it may cause the traffic congestion downstream at some place in a future time point. Thus, we need to consider both of them.
Okay, thank you.
No problem. Thank you very much.
Any other questions? If not, I guess I'd like to end over here. We will see each other. Hopefully, I'll see you guys in 2 weeks. We have this seminar series every 2 weeks. I'll see you next 2 weeks, and stay safe, be safe, and be healthy. Thank you. See you all.
Thank you. Thank you, guys. Thank you, Dr. Ma.
Thank you.